All right, everyone, quiet down, quiet down. So rowdy today. Gonna talk about computer vision some more. Let's just get into it. So we have some logistics stuff. So homework 2 is out right now. It is not due this Thursday. It's due a week from this Thursday. We're gonna cover some stuff in lecture today that you guys need to know for it, so we delayed it a little bit. It's also going to be a little bit longer, so it's good that you guys have a little bit of extra time, basically. We also have this new Google group. It is going to be used instead of Mattermost for asking questions. You can still chat on Mattermost or whatever. I feel like there were some good interactions that happened on Mattermost. It just wasn't ideal for a lot of the stuff that people care about. I think for the Google group, by default, all of your email settings are set to get notified anytime anyone posts anything. You may want to change that. You should be able to get to the Google group just through your UW Google ID or something. I don't know, you guys know the drill on that probably. I think also Kiana changed her office hours to be a little bit later in the week. I think she'll send out an announcement about that because there wasn't any homework when she was going to have office hours. So this way you guys just have a little bit more of quality interaction time with her. Are there any questions about, yeah? Sorry, one more time? I don't know. My hope is that Mattermost will sort of gracefully die and we will all move away from it and go to the Google group. I am going to keep checking it because I imagine that some people will keep posting in it and expect responses, and I don't want to just like leave people hanging. But as much as you can, try to use the Google group for asking questions because it's way easier for other people to go in and see what kind of questions people have, what the answers were, things like that. Mattermost just threading did not work out at all. So, you know, people can still use it like to find project partners or, I don't know, do whatever people do on chat things. Anyone else? All right. So let's talk about what we talked about last time because we didn't finish it, so we're going to keep talking about it and just do a little bit of review. So we talked about how we basically wanted to find key points or features in images, places that are sort of unique to the image that will be easy if we want to accomplish some task, like matching up two different images to form a panorama. And one of the things we talked about was sort of this self-difference thing where we wanted basically globally unique image patches, but we would sort of settle for basically image patches that differed from themselves by some significant margin. And that just means sort of moving around the image patch a little bit and figuring out this self-difference thing that we talked about. And we talked about how we can basically approximate it using this structure matrix. And this structure matrix is basically a weighted sum of nearby gradient information for every pixel. And we talked about how basically the structure matrix summarizes the nearby gradient information. And what we want to do is basically figure out if there are some large gradients in multiple directions. And if there are, then we know we're basically at a corner. And so what we're going to do is take the eigenvectors and eigenvalues of this matrix, and we can figure out what the main directions of gradients are in this sort of nearby little pixel area. And we can also figure out how strong those gradients are. And basically what we're actually interested in is the second eigenvalue, because the first eigenvalue will be the direction of sort of most variance, and the second one will be sort of perpendicular to that, the direction of smaller variance. So what we want is for the second eigenvalue to be large, because that means that basically not only is there a strong gradient in one direction, but there's a strong gradient in multiple directions, and that's why both of these eigenvalues end up being large. And we talked about ways to approximate this. So you can actually take the eigenvectors and eigenvalues of this structure matrix. It's in practice actually not that hard. The thing is, when people were sort of first coming up with these algorithms, computers were slower and they didn't want to do square roots basically. So taking the eigenvalues of that matrix involved like one square root operation, and people were like, oh no, we can't do that. So they came up with all of these methods of basically estimating the size of the smallest eigenvalue, or coming up with some estimation that basically would say that if this thing is large, then the smallest eigenvalue must also be large. And so we talked about the determinant and the trace of this matrix, and calculating the determinant and trace of a 2x2 matrix is easy. It's just some multiplications and additions, or maybe a subtraction thrown in there. So it's a lot easier than taking that scary square root that people didn't want to take to actually figure out what the real eigenvalues were. So we're going to have a couple basically methods of estimating some responses from this structure matrix. And in particular, basically both of these estimates will be large when the second eigenvalue is large. And that's what we really want. We want basically a point in the image where the structure matrix gives us a large second eigenvalue, because then we know that that's a corner from all of the other things that we were talking about. And so this is basically the rundown of the Harris corner detection algorithm, where we're going to be calculating these derivatives. Do we have a question over here? Yeah. So alpha is just some scalar factor, and in practice, it's usually pretty small. It's set to 0.04 to 0.06 or something, so it's just a really small scalar. And this will be useful in the homework, and when it comes up, I will tell you again what alpha is. So you don't have to worry about it too much, but that's just, I don't know who came up with these weird sort of estimates or why they chose these ones in particular. There are a bunch of different ones of these, basically, but these seem to be kind of the two most common ones, basically. Good question. Huh? There is some intuition that has to do with basically the ratio of the two eigenvalues with each other. And importantly, if that ratio is high, then the first eigenvalue isn't going to be like way bigger than the second eigenvalue. Things like that. I tried to gain some intuition by basically doing out some of the math for what happens when you like square that, and it just ended up with a bunch of mess. And I looked around a bunch and tried to figure out what the intuition was and couldn't. But it is pretty easy to see that basically for both of these equations, if we have a small second eigenvalue, this equation will be small. So if, for example, in this one, if lambda 2 is small, then this is going to be small, whereas lambda 1 might still be large, so this ratio is going to be really small. I'm not sure what this same argument is for this one, but I'm sure there's something similar, basically. So alpha is really small in this one. So this term is basically going to be small. And if lambda 2 is small here, then this is going to be small. So there's some kind of intuition for why this is the case. But these are sort of the things that people use in practice. So our Harris corner detector is basically, we're going to calculate the derivative, which we know how to do using Sobel filters over the image. We're going to calculate these three measures, basically the derivative in the x direction squared, derivative in y direction squared, and derivative of x times derivative of y in y direction. We're going to calculate these weighted sums, because remember, this structure matrix is a weighted sum of nearby gradient information from that pixel. And in particular, it's easy to calculate this weighted sum if we use a Gaussian, because we already have this Gaussian filter, which is basically looking at nearby pixels, adding them all together, and then putting that result somewhere. You could also use a box filter, presumably. That would just be a more even distribution of weights over nearby pixels, when often in practice, basically closer pixels are more strongly correlated with the pixel that you're looking at. So really what we want is kind of this smooth gradient function. So using sort of a Gaussian smoothing function works well for calculating these weighted sums. And then we're going to use one of these estimates to basically find places where the second eigenvalue is large. And we're going to do some non-max suppression, just like we were talking about with canny edge detection, where basically we only want local maxima. We don't want a bunch of strong responses all in the same place. So does the Harris corner detector kind of make sense to people? People get what's going on? Cool, you're going to be implementing it. So you better know what's up. And then we talked about basically we can find these corners in images, and we're pretty sure that these corners are going to be good for matching together different images, for example, because they might have some sort of unique properties. We still need a way to basically represent each of these image patches. And there are a bunch of different ways that we can think about these descriptors. So one really basic one is just kind of looking at pixels and what their values are. And then when we're doing this matching, we just want to find basically patches of pixels that look pretty similar to each other. And there are a bunch of ways of doing this. We can think about L2 distance, which is what we have up here. We can think about L1 distance, would just be the sum of absolute differences, which is what you'll be doing in your homework. Things like that. And there are some problems with this, and there are some ways that we can talk about overcoming these problems, and we'll go over that a little bit more later too. We also talked about basically transformations that we can do to images, because we're going to have these two images where we have matching patches in both images, and we're going to have to figure out basically how to blend those two images into a single image. And so we talked about basically there are a bunch of different transformations that we can think of in terms of matrix multiplications. And in particular, we're going to take a matrix and multiply it by a point in one image coordinate system to get to a point in the other image coordinate system. So there are a bunch of transformations. These are all affine transformations, which means they all come from some general 2x3 matrix. And we also talked about just sort of a cool property of affine transformations is that if we combine a bunch of these together, they're still affine transformations, which is fun. And we talked about basically, we have to be able to multiply these by each other somehow, and they're all 2x3 matrices. So to multiply two affine transformations by each other, we just add on this third row, which is basically a couple zeros and a 1. And when you actually do out the multiplication, you can see that everything works out the way you would expect it to. And we also talked about this new transformation, this projective transformation, where we aren't preserving basically the parallel lines that affine transformations preserve. We can actually have sort of this skewing or warping. And this affine transformation uses a 3x3 matrix to do this transformation, and it uses homogeneous coordinates. And we talked about basically what that means is that pixels, yeah, you have a question?
Yeah, so
Okay, so I mean, each of these is basically more and more general versions of each other, but the simplest thing is like if I were pointing a camera at this wall, and then I moved over a little bit and twisted the camera, that would be a projective transformation, because basically the things that are far away have started to spread out a little bit, whereas things, so basically if you think about these parallel lines on the wall, they would be sort of getting closer to each other and sort of spreading out as they got closer to the camera over here, whereas when I was sort of facing straight on, they are just still parallel. Affine transformations, I mean, so translation and sort of like these first three are pretty easy to kind of imagine from that camera perspective. It's like I'm still facing perpendicular to the wall. I can move it around as translation. I can sort of go in and out or rotate it. I'm not sure when the skewing kind of transformation would happen with a camera. I might have to think about that a little bit more, basically. But basically, projective transformations happen anytime, or sort of one way to think about it is basically if you have a camera and you're taking a picture of a planar surface, anywhere you move that camera can be represented as just a projective transformation back to a single location of that camera. And that's why we talk about them being useful for panoramas, basically, is if we can sort of assume that the thing that we're taking a panorama of lies on a single plane, then any of these pictures that we take, we can all warp them back to basically our first image plane with just these projective transformations. So that's super useful. Does that help a little bit? Cool. So yeah, we're going to talk about this projective transformation. And we talked about homogeneous coordinates a little bit. And basically, all this is we're representing 2D points as basically having three coordinates. And they're going to be they're going to be equivalent basically up to a scalar multiple. So in homogeneous coordinates, basically, you have this x, y, and w. And you can think about x, y, and w as representing a vector. And the actual point that we care about is the x and y point when we just divide sort of this vector x squiggle by the third term, by w. And So this kind of makes sense when we were talking about cameras. Basically, we're projecting the three-dimensional world onto a two-dimensional plane. And so every sort of point along this vector basically along some vector that's basically shooting out from your focal point or your aperture. Every point along that vector basically corresponds to the same point on your image plane. And so that's kind of some intuition for where these homogeneous coordinates come from. Yeah. Well, we're talking about images. So with a single image, we never really had that information anyway, basically. So are you talking about like filters and stuff? Yeah, so the focus things, basically, that all comes from having sort of a focal point or an aperture that isn't infinitesimally small, basically. So as soon as you have an aperture that's basically any size, we have to start focusing light from multiple parallel paths onto the same point. And this is kind of what we talked about, like with your eye, you have this lens that can change the focus. And basically, it's this trade-off where you want to start letting in more light, so you have to focus on a single depth of field. So that's a little bit different, but yeah. All right, so going back to basically homographies, this projective transformation basically can be represented by this matrix H. And in particular, to project a point from some old coordinate system into some new coordinate system, we're going to multiply it by this matrix H. And remember that our output is still going to be in homogeneous coordinates, which means that it's all the final x and y values that we care about. We're just going to take these results and divide it by this w prime. And in particular, what that means is basically this whole vector is invariant to multiplication by some scalar, which means that this homography is also invariant to multiplication by some scalar. So some projective transformation, some matrix H, does the same operation when we're talking about projective transformations if you multiply it by some scalar value. It can be thought of as basically the same transformation. And that's going to be important later on when we're trying to estimate these things. So we talked about basically how we have a bunch of these different transformations, and they have different degrees of freedom. And in particular, since H is equivalent up to some scalar value, we actually only have 8 degrees of freedom for H, which is nice. And we have some degree of freedom calculations for all of these other transformations. And so we have a bunch to choose from when we're thinking about stitching together these panoramas. So one thing we can say is like, OK, let's just imagine that what we want is an affine transformation when we're stitching together these panoramas. How would we figure out what that affine transformation should be for 2 different images? And basically, what we're going to do is take the matches that we found using our first, we ran this corner detector, and then we extracted some features at that location. And we match them together in the 2 different images. And now we have a bunch of these matches. So we can start thinking about how can we calculate or estimate this affine transformation A. And so in particular, with one match, we have 2 different equations that we get. In particular, we get sort of this transformation of the x-coordinate, and we get this transformation of the y-coordinate. And we know that these transformations, or sort of we're putting this assumption out there, that these transformations come from some affine matrix. So what happens next? That's what we're talking about today. We're going to go more into stitching. We're going to talk about this Ransac algorithm for estimating these matrix transformations. And we're going to talk about a couple other cool ways of extracting features and looking for key points in an image. So getting right back to it, we have this affine transformation. And with one match, we basically get a couple of equations that start to help us estimate what these parameters are that we need to know. And basically, we can organize this as a linear system of equations. And we're going to basically reorganize it into these matrices M, A, and B. because we're pretty good at solving these linear systems of equations. And in particular, if A is unknown, but we know M and B, we're good at figuring out what A is by solving these systems of equations, by doing these matrix transformations. So does everyone sort of see basically how we've taken these equations and encoded them in these matrices over here? Does that kind of make sense to people? So basically, we have these equations of, we have two matched points. So we have the x-coordinate at one point and the x-coordinate in the other point, and my is the y-coordinate in the other point. And we know that we're doing a affine transformation to get between these two matched pairs of points. So we can basically fill in what that matrix multiplication of that affine transformation would be, and that uses these a sub 0s, a sub 1, 0, et cetera, the coordinates of that affine transformation matrix. And so what we're going to do is basically put these affine transformation coordinates as this column vector in A, and we're going to use M to basically encode the things that we know about this linear system of equations. So in particular, to get nx, we have a0, 0 multiplied by mx. So we have mx1 here, which is sort of the x-coordinate of the first match, and that would get multiplied by a0, 0. And then you have my1, which gets multiplied by a0, 1. Hey, that's right here. And then you have a bunch of zeros. Then you have 1, which gets multiplied by a0, 2. That's right here. And then you have a bunch of zeros. So basically, you have this sum at the top should equal nx1, which is what we have here, et cetera. So we're basically encoding these constraints into these matrices, and we know the values for all of M and for all of B, and we want to figure out what the values are for A. And so this system of equations can be solved if the system is basically exactly determined, or even if it's overdetermined, by doing the same process, where basically we have our equation right here. We're going to multiply both sides by the transpose of M, and then we're going to multiply both sides by the inverse of M transpose times M, and we basically have A in terms of this matrix multiplication on the right-hand side. And this works if M is sort of exactly determined. So we'll get basically the exact solution to it. And it'll also work if we have an overdetermined system of equations. And so that's kind of weird. Basically, if we have a bunch of entries in M and a bunch of entries in B, we have this overdetermined system. And in particular, we're not necessarily going to get an exact solution that makes all of these equations that we have up here turn out to basically get the right values. And so by doing our solution in this fashion, what we actually end up doing is basically solving this least squares problem, where if we have this overdetermined linear system, we can't get basically exact solutions, so we might want to minimize some kind of error. And one thing that we can think about is basically minimizing squared error. So we have our exact, our knowns B, and we have our knowns M, and we're going to be multiplying them by some unknowns A. And we want these two things to be equal, but we can say, instead of being equal, let's minimize how far apart they are when we take the L2 norm of them. And so basically what we can see is, with doing a little bit of algebra, is that solving our system in this fashion corresponds to this least squared error. So if we sort of take the square of this subtraction and do some matrix. So some of this stuff gets a little bit hairy when we're talking about matrices. It ends up being basically that matrix algebra looks a lot like normal algebra, but sometimes you just throw in some transposes. It also ends up being that when you take we'll have to take derivatives at one point. When you take derivatives with matrices, it also ends up being a lot like taking the derivative of just normal algebraic equations, but sometimes things that are squared are really M transpose M, and you think of that as being sort of M squared or something. So we'll see what happens. But basically, we want to square this subtraction, so it ends up just being this matrix transposed multiplied by itself. And we sort of do this matrix version of FOIL where we're doing first inside, outside, last. We get, again, this sort of extended matrix equation, and we can start combining some of these things together. So it actually sort of looks like FOIL, where we have, b squared. Let's see if that goes away after a second. Nope. So we have b squared. We have 2 times a mb, and we have kind of like this ma or am term squared. And we want to minimize this least squared error, and so this equation that we have here is equivalent to this least squared error. So what we want to do is find a place where the gradient is 0. And we know that that's what we want to do because this is a convex optimization problem. So basically, if we find a local minima, we know that it's a global minima. And if we find a place where the gradient is 0, we know that the squared error at that point is the lowest possible value. People have taken some machine learning before, right? Sort of understand a little bit of what we're talking about, this convex optimization stuff. If not, basically, yeah. Yeah, exactly. So we can take the derivative of this top equation and set it equal to 0. And this is what I was talking about, where basically you kind of squint your eyes and pretend like we're just sort of doing normal derivatives. So we're doing this in particular with respect to a. So there's only one a here. So we'll kind of cancel out this 2, and we'll get rid of this a, and we just get left with mb. And there are 2 a's here, so this is kind of like a squared. So we'll just like get rid of 1, and we end up with basically the square of m still multiplied by a. And we want to set that equal to 0. So we want a place where the gradient is 0. And then we just do some sort of normal matrix algebra to bring mb over to the other side. And then we have to take an inverse of this and multiply it by both sides. And we get sort of this equation that we started out with. Yes? All of the stuff that we're talking about, I don't think we do any kind of regularization on. And basically, there are some times when these matrices won't be well conditioned and you won't be able to find a good solution. Basically, some of these inverses start breaking down and stuff. It's actually better if you have regularization, because I think you have some results that basically these inverses are more easily doable. But we're not going to be doing any regularization for this. When we start talking about neural networks, we'll start getting into some regularization stuff. But then it's all gradient descent, so it won't play a factor in this. Yeah? Yeah, so sometimes basically there isn't some solution to this overdetermined system, or there's something that goes wrong basically, and there's no possible inverse. And in practice, basically you've picked the wrong points to try to figure out the transformation from, and you should pick different points. So we're not going to worry too much about that. Basically, the answer is just like try again with some different points and see what happens. And in practice, basically, you'll encounter it a little bit in the homework. It does happen, but it's not super common that this m transpose m is not invertible. Cool. So we're going to be doing this least squares regression, or sort of we're going to find this least squares fit for this affine transformation. So it's good to start thinking about basically how well solving this least squares problem does in practice. And basically, say you have some data that you're trying to fit a line to. This is just sort of linear regression. Least squares can do pretty well if your data is pretty well behaved and sort of looks good. And then as soon as you start adding in some kind of noise in your data or any outliers, you start getting pretty bad results pretty quickly. And in particular, this is because we're minimizing this squared residual. So it's linear least squares. So what ends up happening is a single outlier can generate just a huge amount of error, because the squared error will be just so far away from the line that you actually want to fit. So least squares is like really afraid of kind of just ignoring this point altogether, which is kind of what we think it should do. And so instead, it basically it makes this huge modification to the line that it's predicting, and all of a sudden we have just like something that doesn't really fit any of our data very well. So least squares has its pluses in that it's pretty easy to find this closed form solution to it. And if our data is kind of well behaved, it'll come up with a good solution. And in particular, if our data looks really good, then it'll get this like very nice solution. And it's very bad at handling these outliers in our data. So what we really want is something that can handle outliers, because when we look at sort of the data that we're dealing with these two images, and we have all of these points, and we find sort of the closest matches between these points. We have a ton of outliers, right? Like, you can see like a lot of lines are generally kind of going in the same direction. They're generally kind of going right to left. But then we have like this cluster down here that's all kind of trying to go up into the mountain somewhere. And we have some random points that are sort of making this long downward traverse and stuff. And just some really weird things going on when we start talking about matching up these panoramas with each other. So we have this super noisy data, and we know that there is some transformation, or we're pretty sure that there is some transformation to get from one to the other. We just have to kind of figure out what that transformation is in the presence of all this noise. So what we're going to end up doing is this new algorithm called Ransac, which is a fun name, and it's random sample consensus. So basically, this is an algorithm that's really robust to having a bunch of outliers in the data. And it sort of makes this one pretty simple assumption that all of the inliers in your data are all going to agree. They're all going to be pretty good. They're all going to be pretty well behaved, basically, with respect to each other. And all of the outliers are going to be sort of randomly distributed. So you'll never get a bunch of outliers that all agree with each other on some different interpretation of the data. And if you make this assumption, or if your data sort of behaves in this fashion, Ransac actually works really well. And what we're going to do is basically just try a bunch of different models, basically sampling a bunch of different points to include in our model estimation, and see which ones sort of fit the data the best. So imagine that you're trying to fit a line to this sort of messy data that we have here. And we can kind of tell that basically there's something going on along this axis, and that's probably the line that we actually care about. But then there's also a bunch of noise, and kind of least squares would do some weird thing here. It would probably like end up with a line that kind of goes up and down through the middle or something. So it's clear that this isn't a problem that just throwing least squares at is going to do very well for us. So what we're going to do is basically pick a few points to fit a model to. And in this case, we want to pick the fewest points possible, because we want to maximize our chance of picking a set of points that are all inliers for the data that we have. So with a line, we just have to pick 2 points, because all that it takes to fit a line to some data is 2 separate points. So we're just going to pick 2 points randomly and fit a line to those points. And then we're going to look at all of the points that fall within some error bound, or fall within some distance of this line that we've predicted using these 2 points. And we're going to say that all of those points that fall within that distance are inliers to this model, and all of the other points are outliers. So in this case, we have 4 inliers to this model, and we have a whole bunch of outliers. So this isn't a very good model. And then we're just going to do this a bunch and remember how many inliers each of these models gets. So in particular, if we get lucky and pick sort of these 2 points, we have a whole bunch of inliers to our model. In this case, we have 11. Whereas if we pick a couple other points and they're not very good, we have very few inliers. And we just sort of keep doing this over and over again. And we come up with a bunch of models, and we've remembered which one had the best sort of predictive power with the data that we have, which one sort of most of the data agreed on the most. And this is where this assumption plays a big role. So basically, if you have a bunch of data, even if you have a bunch of noise in that data, if all of the inliers agree on what the right model is, and all of the outliers sort of disagree with each other, then at some point, you sort of hope that basically you keep doing this sort of random selection and fitting this model. At some point, you're going to pick a set of points that are all inliers to the same model. And then all of the other inliers in your data are going to agree and say, OK, yeah, this is actually a really good estimate of what the correct model is for this data. Whereas all of your other models that you're picking, you have some outliers included. And those models are going to be pretty bad. And remember that we're assuming that all of the outliers kind of disagree on what the right model is. So they're never going to basically agree on any of these wrong models, but the correct model is going to have all of the inliers in the data sort of agree with it. And that's how we can recover basically what the correct model is for this data. So the Ransac algorithm basically has a bunch of different parameters, and these are all little knobs that you can basically tune. But the intuition is what we just went over. So we're always going to be keeping track of what our best model was and how well that model fit our data. And then we're just going to loop a bunch of times, and we're going to draw this sample from our data where that's basically the number of points that we need to fit a model. And we're going to fit our model to that sample, and we're going to calculate basically how well that model fits the data. So how many inliers are there within some t distance of our model, where t is some threshold that you pass in. And then we're just going to compare this number of inliers to how well our best model so far has done. And if this new model is better than all of the other models that we've tried, we're actually going to do another round of fitting, where we're going to fit our model to all of the inliers that we found before. So remember when we were here, basically we had this line was just fitting between these 2 points. But all of these other points were inliers to this same model. So this step of the process basically is another round of fitting, where we're going to take all of these inliers and use them to fit a new line using least squares. So we're pretty sure that all of the points along this line that all kind of agree are inliers to the data, are like real sort of data points that we care about. So we should be able to fit a least squares model to these points, and it won't be subject to the same kind of noise that we talked about before, where these outliers can throw it off. So our least squares fit to just these inliers should actually be pretty good. And in particular, it will probably be better than just fitting a point between 2 of these inliers, because we still think that there'll probably be some kind of noise in our data. So we're going to fit our model to basically all, in this case, 11 of these inliers. And hopefully this will actually start correcting some of the error that we have in this current line. And maybe it would shift it a little bit and sort of be down to the left a little bit more or something. So that's an important part in this. We're going to fit sort of our new model to all of the inliers. And then we're going to update basically our estimates for our best fit and our best model. And we also have sort of this cutoff value, where basically we say that if our model is really good, if the number of inliers is bigger than some threshold that we pass in, we just want to quit immediately. We just want to return sort of the current model we have. We're pretty sure that it's pretty good. And so there are a bunch of different parameters that you can tune for this, things like our threshold t, and things like how well something has to fit to just kind of exit immediately. So for this example, I can't remember exactly. I think there might be like 30 points in this or something. So we can be pretty sure that if one of our models has like 15 points that are all inliers to it that all sort of agree together, that is probably a pretty good model. So our threshold, this threshold d that we're talking about, it could be something set to like half of the number of data points that you have, or some sort of threshold. And in particular, we can actually work with values of d that aren't super high. And this process works well even sort of with this extreme noise that we have. So here's sort of a bunch of corners detected in these 2 images again, and the matches that we have between these 2 corners. And again, we see that we have some good matches and some bad matches. And some of the bad matches are even pretty subtle. So it kind of looks like these 2 matches are in roughly the same orientation, but they sort of flip directions. So I think one of these is actually correct. And one of them just sort of goes off the rails. So I think this kind of top one that goes from the top in the right to the bottom in the left is an incorrect match, and this one that's in the top in the left and goes down over here is sort of an actual correct match, where these 2 pixels correspond to the same thing. So some of these are kind of subtle. But when we actually end up running our Ransac algorithm on this data, we can pick out sort of the inliers to this data pretty easily. And in this case, we're sort of drawing them in green and basically ignore all of the other outliers. So in this case, I think probably about half of our data is just noise. And this actually works even at sort of much higher ratios than this. So in some of the panoramas you'll be doing, you have like 300 matches between two images, and you end up with a model that's like 10 inliers or something. But it turns out that those 10 points all agree on what the transformation should be, and none of the other 300 points sort of agree on some consistent transformation. So those 10 inliers are actually really good, and that's actually the transformation that you wanted between those two images. So it works well in sort of these really extreme cases where you have this huge amount of noise, which is cool. So again, we have all these different parameters, and there's some guidance for this when you're actually looking at them in the homework. But basically, there's some kind of general intuition. And basically, when we run this algorithm, we want there to be a pretty high probability of, at some point, sampling the number of points that we need that are all inliers to our model to get some good fit. And oftentimes, you make this assumption that all of the inliers are pretty well behaved, so you can usually set this threshold to be pretty small. For images, I often set the threshold to be about 2 pixels. So if the pixels sort of, when you apply this transformation to them, if they end up about 2 pixels away from sort of their closest match where you want them to end up, you count that as an inlier. And 2 pixels, in these images is pretty small. So we assume that, some of our matches are going to be very close to what they actually should be. N is the number of data points that we sort of put in to fit a single model. And we often want this to be really small. So again, we want to maximize our probability of picking a set of points where all of the points are inliers. So if you have n be sort of higher than it needs to be, every sort of additional point that you add in could be a potential outlier. And in particular, we're dealing with cases where there's a lot of outliers. So you imagine that even if it's sort of 50-50 between outliers or sort of inliers and outliers, every time you're picking additional points, you multiply your probability by 0.5 that you're including some outlier in your data, right? And so if we're predicting homographies, we need 4 different matches. So someone tell me what 0.5 to the 4th is. I don't know. But as you start adding in more and more points to this, or more and more matches to this model, you start decreasing the probability more and more that you're going to pick a set of points that are all inliers. And in particular, the number of iterations is going to be very high for the same reason. It's pretty unlikely to basically pick this set of all inliers, depending on what your data looks like. So you might have to do this a bunch of different times before you actually get lucky and pick this inlier set. And our final parameter, sort of D, this cutoff value, we think that it should probably be a lot higher than basically just the number of points that you need to fit a model. It probably doesn't need to be, like super big. It doesn't need to be like, for example, your whole data set. If you recover some model that fits all of the points in your data set, then you didn't need to do Ransac in the first place. And D could be based on basically some estimate of noise that you might have about how noisy your data is. If you know that about half of your data points are noise and about half of them are inliers, then you probably don't want to set D to be more than half. And in particular, maybe like somewhere around 1/4 or something starts to make sense for that cutoff threshold. Does sort of the basics of the Ransac algorithm kind of make sense to people? Do people sort of understand? Yeah. Yep, I mean, that's literally all it is. There's just a little bit of tuning parameters that we throw in and some early stopping criteria and stuff like that. Yep, that's sort of the whole thing. Yeah. Yep, exactly. Yeah. So that was that last step in the process where basically once we have this initial estimate and we know that it's better, this initial sort of new model that's better than all the other models, we're going to fit the model just again to all of the inliers that model found. And that's, sort of this refinement step where basically you have a bunch of data that all kind of agree, but you initially estimated this model with this minimum set of data. So we might as well re-estimate it again with all of the inliers because we'll probably get some better estimate that's a little bit less sensitive to noise. Cool. So we talked about how we estimate this affine transformation, but we also talked about how in practice, what we really want is probably some projective transformation or some homography. And again, we sort of discussed kind of some intuition for why that is. Basically, if we assume that whatever we're taking a picture of is some flat surface, is some planar surface, then using just homographies, we can project a bunch of different images of this same planar surface onto the same image plane using just these projective transformations. So what we really want is to be able to estimate this homography. And this is a little bit more tricky than our affine transformation because we have this extra sort of constraint that we're working in homogeneous coordinates. So now we have this division that happens where we're basically the point that we are projecting to is divided by this W term. And this W term is also sort of a product of this matrix multiplication. So it looks like basically a system that has 9 degrees of freedom, but in practice, we are making these assumptions about how this is basically the same up to some scalar factor. So what we can end up doing is basically assuming that one of the entries in our matrix is 1, and the most common one to assume is 1 is just H22, because it's sort of in the lower right-hand corner. I don't know, people don't like it. And we're also going to assume that basically this W term that we're passing in is going to be 1 as well. And this is pretty easy to, at least sort of the second one is pretty easy to enforce because we're creating these, and all we actually care about are sort of the x and y coordinates in an image, and this W term doesn't really make any difference to us anyway. We just know that we basically have to normalize by what W is to recover our original x and y coordinates. So if we want to make sort of this x tilde vector, all we do is plug in our original sort of x and y coordinates in the image and just plug in a 1 here for W tilde. And now we have a little bit simpler of equations here because we've basically gotten rid of this term for MW. So we just have HO2 here. And we've gotten rid of this term for H22 multiplied by MW with just this 1 here. And so again, we're going to have the same sort of thing where we have this system of equations that we want to solve. We're just going to do some algebra here. And in this case, we're going to do it on the x coordinate of some point that we're projecting between these two systems. And basically, when we multiply through, we have this same sort of equation where we have a bunch of different unknowns and a bunch of knowns. And we can form these same sort of matrices for homographies like we did for affine transformations. And this is pretty cool because remember that we were working in these homogeneous coordinates where everything was sort of the same up to some scalar. And a lot of times that would pose some problems for trying to estimate these homographies. But just using sort of these basic assumptions that H22 is 1 and this W component is also 1, we can come up with still a way to estimate this. And we can do basically the same process where we do these matrix inversions to get this least squares fit. So again, we're doing the same procedure where we're solving, our homography time, or sort of this M matrix that we made up times our coordinates of our homography equals basically this B matrix that we made up as well. And these are all based on our systems of equations. And again, this is going to be exact if we basically use the same number of degrees of freedom that we have, if the number of rows in M is equal to 8. And it's still going to be this least squares fit to this problem if the number of rows is more than 8. So that's cool. There might be some issues with doing it like this. Can anyone think of some issues that might result from this kind of solution? So basically, we made this assumption that H22 in this matrix is going to be 1. And that's not always the case with homographies. And in particular, a projective transformation is just any 3x3 matrix. It can be totally general. So this H22 component might actually be 0 sometimes. And if it is 0, all of this kind of falls apart and things go poorly. And when you try to invert this matrix, things are going to break. And in practice, it's pretty rare for H22 to actually end up being 0. So it just kind of doesn't matter that much. And since we're doing sort of this Ransac thing anywhere, where we're sampling a bunch of points and just trying them out, sometimes basically something will happen with this matrix inversion and it won't work very well. And you can just kind of ignore it and go on to the next one. So it's cool. And you shouldn't basically use this in general for calculating projective transformations because it can fail at times. But when we just want something sort of quick and dirty, this works pretty well, especially for doing your homework. So you might want to remember these slides. So now we can finally sort of combine together a bunch of these different ideas that we've been talking about for a long time. We had this corner detection thing that we're talking about, so we're going to find corners in both of these images. We're going to figure out what these descriptors are in both of these images. We're going to match the descriptors together using some kind of distance metric. We talked about a few of those. We're going to use Ransac to find these homographies between images. And finally, we're just going to be able to stitch these images together. And in general, this is sort of the assumption that I was talking about before, where we're using this homography because under the assumption that basically we're taking pictures of some planar object or some object plane, we know that there has to be a homography that describes the transformation from the coordinate system of one of these images into the coordinate system of this other image. So in particular, these, and this is with respect to any sort of camera orientation or angle or et cetera, et cetera. So this is actually a really general assumption that goes beyond, general, if you're taking panoramas, you just click the button and then turn a little bit and then click it again and then turn a little bit. So you don't even need the full sort of strength of this assumption, which is much stronger. But it's something that we can sort of think of as maybe being useful in this case, where basically any orientation or sort of direction of this camera, as long as it's taking an image of this object plane, and any orientation and location of this camera, we'll end up with two images where there's just a homography that projects back and forth between those two images. So that's a pretty cool thing just to kind of know about, and we'll see why that breaks a little bit later. But in practice, sort of our algorithm works pretty well. So we have this image, and we're going to find a bunch of corners in it, and we're going to find some other image and kind of warp it and just sort of paste it in there. And we're just going to keep doing the same thing with a bunch of different images, and we sort of end up with this cool panorama. And you guys will be doing this exact one in your homework, so you'll start thinking about this kind of stuff. Is there one more? Oh yeah, one little corner one, just adds on a little bit. So this is pretty cool. We can see that maybe we're not quite done yet. It is we just sort of applied the transformation and just kind of pasted the image right on here. So we can see a couple little borders and stuff. It looks like this fit didn't work out entirely perfectly right there. But maybe it sort of worked out pretty well along this sort of path. So that's something. So there are some more complex, basically, stitching mechanisms that we can imagine for basically getting these images to kind of fade in between each other nicely. And you guys can kind of look up that stuff on your own, too, if you're interested. But basically, oftentimes, people will sort of make one image fade into the other one just by using some alpha blending along these seams. Another common thing is to look at basically doing multi-band stitching, which is look at the low frequency components and kind of blend them together, look at the medium frequency components, kind of blend them together, high frequency, blend them together, all separately. And if you do that, you end up with a lot less artifacting than you might otherwise get when you're kind of stitching these things together. But this, even just sort of pasting the image right on there, this kind of looks cool. And you could imagine, so with some quick kind of fixes, you could start to get a really good looking panorama. Did you have a question? Yeah, well, and in practice, this one isn't, right? So this is this mountain, and you can start to see basically where some of this breaks down a little bit. So I think that's probably what's going on here, basically. So as long as everything's pretty far away, everything that's far away sort of acts like a plane. Basically, if everything were at infinity, you can imagine that that's like a planar surface. And then you don't start to get effects from moving around your camera too much and stuff like that. Now, all of sort of the background stuff, the whole structure of the mountain does pretty well under this assumption. But once we start basically getting to the foreground, where we're talking about basically the place that's kind of near your feet, some of this starts breaking down a little bit, and the projective transformation can't quite deal with that as well. So that's why we have basically this image is really well aligned with the rest of the image when you start talking about basically like in this region, but it starts to get kind of messed up when you start talking about the location that would be sort of closer to you, where this planar assumption might start breaking down. So yeah, basically we're seeing what happens as this kind of starts breaking. But also, like, this is, it looks like kind of a pretty good panorama, but we start to see some limits of using just these straight projective transformations when we're doing this kind of stitching. So in particular, you're taking a bunch of images of the same thing, and we're going to stitch them all together into one image plane. So we have our first image, and we have sort of our second image, and our third image, et cetera. And we want to stitch these together into some sort of panorama. And in particular, we're sort of going to take the first image that we sort of looked at and imagine those as being the kind of right coordinate system. And we're going to modify all of the other images to fall in that same image plane. So in this case, we're just going to imagine kind of the image plane being offset a little bit, just because it's a little bit easier to visualize. But imagine this is just sort of being the image plane for the green image, and we're just going to paste all of the images onto that plane. So in particular, the green image doesn't really move at all. The pink image, we're sort of going to project these lines from our focal point onto the original image plane, and that's where we sort of stitch that image onto this new image plane. And we're going to do the same thing with this blue image. So we start to see this weird relationship emerge where basically the green image, all of these images are basically the same size. The green image is going to take up sort of this like middle, third, or maybe basically like a middle third of this final image. And the blue image is really big, right? And so is the pink image. They're both taking up about half of this image plane that we're talking about. So we're starting to get basically this warping that happens when we're talking about stitching these all to the same plane. Because basically all we've done is just made our image plane a lot bigger. And we get this weird thing that starts happening with cameras, where basically you've probably taken a picture before, and everything that's kind of in the middle of the picture looks pretty normal and looks about like how you would sort of see it. And things that are sort of off to the sides of the image start to get this weird warping, and kind of stuff starts happening to them. And this sort of makes sense because if you project it out, sort of rays from your focal point to sort of locations in the middle of the image, they're all pretty close to each other. As you start sort of projecting out those same rays that might not differ in angle too much toward the edges of the image, those are going to correspond to pretty large changes in terms of distance in kind of the real world. And that's what starts to happen in this image, where basically we have, the middle images are pretty small. So I think the bounds of kind of our first image are just like this small area. And then we get this image that sticks way out in sort of our field of view. That's kind of near the edge of this. And in particular, we can kind of see that like this only really works as long as the images that you're taking a panorama of and taking a picture of are kind of in front of you. And you can imagine that like if you wanted to take an image sort of over here, all of a sudden there's no real way to like draw this line from your focal point through this image that ever intersects the image plane that we actually care about. So you start to get basically this breakdown in terms of what you might want to take a panorama of versus what our assumptions or what our current setup will sort of allow you to take panoramas of. And that's one of the limitations of kind of this assumption that we're basically taking pictures of this planar object. So what are some ways that we can deal with this? Or kind of what happens when we actually see this in practice? So imagine that we want to take a really big panorama of just a big area, and we're kind of going in a circle. As we start kind of getting to the sides of this panorama, we're going to get a huge amount of warping that happens, because again, we're trying to just imagine like this sort of fisheye camera or something that's taking in a bunch of different, taking in this huge field of view and taking an image of this really large field of view. And we start to get the same kind of warping that you might imagine with a fisheye camera. And then we just kind of start breaking as we try to stitch more and more. The algorithm just kind of quits, and it doesn't do very well. So we want some way to kind of fix this problem, because in practice, you guys probably want to stitch more panoramas together than just like a couple images that are all kind of the same thing. So what we're going to do instead is think about this, instead of as projecting onto the same image plane, we're going to think about projecting onto an image cylinder. And so in particular, basically, we have all of these images, and we want to stitch them all together. So instead of thinking about basically one flat plane, let's think about a cylinder, and then let's think about sort of unrolling that cylinder afterwards. So each of these images we can imagine as basically, instead of taking a picture of a planar object, you can imagine if you're inside of some big cylinder, just sort of turning around and taking pictures of a cylinder. And so we can project each of these images onto this cylinder. And now when we do this projection, all of these images are basically taking up the same amount of like space on this kind of image cylinder that we're talking about. And so that's pretty cool, because that's going to start eliminating some of this weird skewing and warping that was a problem before. So we can take all of these images and project them onto this cylinder, and then kind of unroll them all on that cylinder and stitch them together, sort of these new versions of these images. And in particular, there are a bunch of equations for doing this. But basically, what you can kind of think about how we're doing this is we're finding the x, y, and z coordinates for where this point will fall on this image cylinder. And then we're unrolling the cylinder. So it's sort of this two-step transformation where we're sort of projecting each point in our image onto x, y, z space where it falls in the cylinder. And then we have to do this unrolling that happens when we actually take this cylinder and kind of lay it flat. And so these equations might also be useful for your homework. So maybe remember where you saw them. And in particular, these equations are going to rely on a couple of different things. So sort of this angle makes sense, where we're looking at the angle between sort of the center point of the image and what point we're currently trying to project. So this theta, it makes a lot of sense that that's kind of involved. Another thing that's also involved is basically this focal length. So we talked about basically before, when we're forming these images, we have some focal length that is sort of the distance between our aperture and the plane on which we're collecting images. And in the past, we sort of talked about how we can think of basically projecting that focal length either backward into the internal body of the camera or sort of forward. And all of these images that we've been showing are using this pinhole camera model, where we're talking about basically this negative focal length so that we can have the image plane kind of out in front of the camera. And it's a little bit easier to sort of think about and reason about, because you don't have to flip everything over and like talk about images forming on the back of this camera and stuff. That's annoying to do. So it's pretty clear that this angle plays a role, and also this focal length is going to play a role, because obviously if this focal length were a lot longer or shorter, it would start changing these angles that we're talking about and things like that. So in practice, we're going to take these images and project them onto the cylinder, and it's actually really dependent on this focal length. And everything else in here, we sort of know, right? Like all of these equations are dependent on the coordinates that we're looking at and sort of the center of the image. The coordinates we're looking at, the center of the image, theta is just dependent on them. These are just dependent on the x, y, and z coordinates. But we have this sort of unknown focal length f in here. And so the different projections that you get when you kind of project these images onto cylinders are super dependent on what this focal length is. So if your focal length, if you set it to be really small, the projection might start to look sort of weird. Here is f equals 1,000. Here's f equals 1,400. Who has a guess for what a really long focal length will look like? What if you had a focal length of like 10,000? Does anyone know what the image will look like? Super long? Anyone else? Yes, exactly. Because Really big cylinders basically look like flat planes. So it's just the same thing as basically projecting this image onto this like really big cylinder that is at that point just sort of looks like a flat plane. Sorry, I think you were first and then you had a question. Yeah. Yeah, so this picture doesn't really show it, but basically the cylinder, you can imagine it as going through the center point of this image. So the cylinder is dependent on the focal length, basically. Yeah. Yeah, so that's one potential thing that we could think about for, yeah, warping that might happen when you kind of do this tilting. So yes, in particular, basically, this is the assumption that basically everything that you're taking a picture of lies on some cylinder. There are more general assumptions that you could make since the world is sort of spherical in practice. That would be a good extra credit problem. So how does this work in practice? I have estimated the focal length for these images to be about 1200, and this focal length is in terms of pixels, which is kind of weird because normally focal lengths are like in terms of millimeters. But by stitching together a bunch of panoramas, basically at different focal lengths, I was able to estimate what the actual focal length is for this camera in pixels. There are more exact ways of calculating this that rely on basically this image calibration, where you take a bunch of pictures of this kind of gridded pattern and do some calculations. So I just sort of estimated for these, but basically, you know, this warping to these images is actually pretty small. You know, we've done this projection onto the cylinder, and it's not actually changing these too much. But when we actually start stitching these together, you know, we can start basically stitching more and more of these on top of each other, and we get a pretty good image that has a really wide field of view. And actually, you know, there still is a little bit of warping, so maybe I didn't make my focal length quite small enough. Maybe this is a little bit too large for this actual panorama or this camera. But this works pretty well in practice. So again, this is just using the exact same stitching we were doing before, where we're assuming that there's some homography between these different images. But just by sort of pre-processing with this little bit of warping, we can get really good results on this panorama, where before we sort of had this skewing that happened that kind of ruined everything. So that's also going to be part of your homework. Just, you know, new things to think about with regards to panoramas. So man, this is so cool. We're like making these panoramas. This is like awesome. We have nothing to worry about. It turns out that we still have a bunch of issues. And you know, one potential thing you might think about is like, okay, we have these descriptors that we're matching between different images. And right now we're just using pixel values, and that's not actually like very smart. So in particular, like these pixel values are going to be dependent on a lot of different things. One of the things that they're going to be dependent on is just like lighting. So, you know, when you take two different pictures sort of in quick succession, your camera's really fast. It's even faster than you are. So it'll like start changing settings all the time. And unless you're like really good and you like set all of the settings manually, if you just have it sort of on auto mode, it's going to like change the aperture, and it's going to change the shutter speed and all of these different things. And you're going to end up with like a picture that has totally different lighting characteristics. And now we have, you know, maybe these two different patches in our two images that are actually the same place, but they look totally different if we're just looking at pixel values. So maybe we want to start thinking about features that have some invariance to this kind of change between images, some invariance to this kind of lighting. So one potential descriptor that we could use is called histogram of oriented gradients. And this was introduced by Dalal and Triggs for person detection in 2005. And in particular, we're not going to look at pixel values, but we're going to look at something that you guys should be used to by now, gradients. We're going to look at, in particular, gradient magnitude and direction. So for every pixel, we're just going to look at sort of a bunch of nearby pixels. And you guys are pretty good at calculating gradients. So we're going to calculate the gradients for the image and look at sort of nearby pixels. And we're going to bin all of those gradients into some cardinal directions. So in this case, you can sort of see what binning would look like if we just had 8 different directions. So any vector that sort of, I'm going to do this with my mouse because it'll be a little bit easier. Any vector that kind of falls within any of these directions will all be binned into this same sort of cardinal direction of being sort of up and a little bit to the right. And then we're gonna aggregate these gradients across larger blocks to make a histogram. So we're gonna have, so many gradients that were in this direction, so many gradients that were in this direction, so many gradients in this direction. And then we can normalize these gradient magnitudes to start eliminating some of this dependence on lighting conditions. So you can imagine that basically changing the lighting in the image might change how strong a gradient is. For example, if you have some light object and some dark object in the background, if you turn up the light on just that light object in the foreground, it's going to make that gradient stronger, but it's not going to change the directions of the gradients in the image. So we're going to normalize these gradient magnitudes, and there's a bunch of different ways you can do that. But basically, any kind of normalization to, say, some unit vector or something like that will start to get rid of some of these dependencies on lighting conditions. So now all that really matters is just sort of the direction of gradients in an image when we're talking about extracting these feature descriptors. So we've gone from basically using exact pixel information to using this histogram of gradients. And now we're starting to get some invariance to lighting changes. And Dalal and Triggs actually use this for recognizing people. So they wanted to basically find pedestrians in images. So they were, even in 2005, they were thinking about self-driving vehicles and how they didn't want to hit people. So they trained an SVM on sort of these kind of features to look at an image and tell if basically a small image patch was a person or was something else. And so in particular, we have here sort of a person and the features extracted from our histogram of oriented gradients. So most of these features are basically just little vectors in a bunch of different directions. And the image that we see on the right is the features from the image on the left, but weighted by how much this SVM is responding to each of them. And so in this image, just from sort of this picture, it doesn't really look like a person to you and me. But when we actually look at basically what the SVM is looking for, and we weight these gradients by what this machine learned model is looking for, we actually kind of can see a little person in here, right? So it starts making sense why these features actually make sense in terms of looking for something like a person. And it also is pretty cool that basically these features have built in this invariance to different lighting conditions. So even if it were sort of a lot lighter or a lot darker in this scene, this person would probably produce a similar sort of feature vector. And then when we ran this SVM over the image, we would find similar features and hopefully detect them as a person, which is cool. Yeah? Yeah, great point. So this is a histogram of oriented gradients. So what if you took this person, turned them over on their side, right? HOG features in general are still dependent on orientation. So they are not rotation invariant. And that is one of the problems with them. In general, if you're looking at pedestrians that are sort of walking around outside, they're mostly just kind of upright and often in sort of the same orientation and stuff. So it's a little bit more of a constrained problem. But if we start thinking about if we want to detect objects, in more complex orientations and stuff like that, sometimes these HOG features start breaking down. So that's one of the things we're going to talk about now. With corners, with sort of our Harris corner detector that we talked about before, we already have some of this rotation invariance. So, for example, our detector will detect this as a corner, and it will detect this as a corner. But it's not really invariant to large changes in scale. So if we zoom way in on this line, and we're looking for corners, well, now all of a sudden, this exact same point just sort of looks like a line, because it's kind of this smooth curve that we're looking at. So our Harris corner detector is not, it is rotation invariant, so it'll still detect corners at different rotations, but it's not invariant to scale. And our HOG features are not rotation invariant, because if you rotate the image, all of these vectors get rotated along with it. So we have a couple new problems that we sort of might want to address, where we might want something that's scale invariant. We might also want something that's rotation invariant. And also, as we talked about before, if we just sort of look at pixels, those are also not rotation invariant. If you flip a bunch of pixels around, you're going to have a really high distance from sort of a matching set of pixels in another image. So in particular, we can think about this new feature space called SIFT. And SIFT is cool because it does a couple things for us. It both finds key points in images, and it also calculates descriptors for those key points. So before we were doing this sort of two-step process where we basically would find corners in an image using Harris, and then we would extract some sort of descriptor on our own. And that might be something like pixel values, or that might be something like HOG features. But with SIFT, we're actually going to do both at the same time. So it's a sort of multi-part algorithm where we're going to first kind of get this scale invariant response map. So you could think of this as kind of like doing Harris, but something that might be more invariant to scale. We're going to find key points in that scale invariant response map. So all of those key points are going to be invariant to scale. And then we're going to extract rotation invariant descriptors from each of those key points. And in particular, we have a couple of things that we care about. We're going to normalize based on orientation, and we're going to also normalize based on lighting. And a lot of this shouldn't be sort of too unfamiliar because we've sort of built up to this point. SIFT is pretty cool. So the first thing that we want to do is extract this scale invariant response map. And how we're going to do that is basically extract a response map at a bunch of different scales. It's not that brilliant. It's just like no one had done it before. So we talked about this difference of Gaussian process before and how this difference of Gaussians can give us information about like cool places in an image, basically. And so what we're going to do is basically just get a bunch of different scales of an image and then extract this difference of Gaussian at a bunch of different values for sigma. So each of these are the same scale, but different values for sigma. So we get a bunch of difference of Gaussian images. And then we're also going to do that at a scale smaller and a scale smaller, et cetera. So basically, we have a bunch of difference of Gaussian images of the image at different scales. And then we're going to look for local maxima, both in terms of location and in terms of scale. So we're going to look for high responses that are high both in terms of where they are in the image, but are also sort of the largest response when you're looking at this image and a little bit smaller of an image and a little bit smaller of an image, et cetera. Question? You're changing the scale of the image. Yeah. So you shrink the image down and then you do the same difference of Gaussians process. And then we're going to get rid of sort of weak responses and edges. And a lot of this should be familiar to you guys already, basically. How we're going to do it is we're going to estimate some gradients. And this is cool because before we had to estimate gradients across the entire image. Now we're just going to estimate gradients at these key points that we've already found using this process. So we have a lot fewer places to estimate the gradient at, and hopefully it'll be a little bit faster. And now we can get rid of sort of the weak responses in terms of sort of the strength of their gradient. So we're going to throw out basically like large patches of sky or something. But we're also going to do this same kind of Harris-like process where we're going to find things that look like corners. And to do that, we're going to do the same sort of thing with this structure matrix. And in this case, we have this new ratio that they're using, sort of this new estimate, where we're going to do the trace squared divided by the determinant. Again, we talked about this before, but like all these things are just sort of estimates for the second eigenvalue. In this case, this is actually an estimate for this term over here, which is the ratio of the first eigenvalue to the second eigenvalue. So R is the ratio to the first eigenvalue divided by, or the second eigenvalue divided by the first eigenvalue. So you come up with some new threshold and basically say that you want this term to be larger than some amount. And if it is, you have a pretty good likelihood of that being a corner. So we do this sort of throwing out of weak responses and also of edges. So we're just kind of left with corners. And now we have to do this feature extraction part. And this is going to look a lot like our HOG features, where we're getting this histogram of Gaussians. But in particular, we're just going to normalize based on what the largest orientation is. So we're going to look at a patch and find a bunch of different directions for our gradient. And we're going to find the peak kind of directions. And actually, we're going to extract multiple descriptors for each patch. And we're going to extract a descriptor for every peak that goes over, or for every gradient direction that goes over 80% of the largest gradient direction in that patch of the image. And then we're going to just extract sort of the same kind of Gaussian, or the same kind of histogram of gradients that we talked about before, but we're just going to normalize it so that the strongest gradient is always in one direction. And then we also have this normalization process that takes care of lighting changes, where we're going to normalize this histogram to be of unit length, and then we're going to clamp by a certain amount, and then we're going to normalize again. And this helps get rid of these variations that are due to lighting. And in practice, SIFT is really cool. It helps us do a lot of things. So here is an image that has a couple little toys in it, this little truck and this little frog. And we can use SIFT features to find these little objects that we care about, even when we have sort of some extreme occlusions and some like big rotations and kind of different orientations and stuff of these objects. We can also use it in this more complex scene where we're kind of trying to recognize some of these rotated objects over here in this image, and we can sort of do it successfully. So SIFT features are like the really cool thing from 10 years ago that we still use for some things, but we don't use as much anymore because now everything's replaced with neural networks, which we will learn about in a week after we do some stereo stuff. That's all.